So welcome everybody to a new edition of our webinar series DaSSWeb. Today we have the pleasure of welcoming João Mendes Moreira. João is Associate Professor at the Faculty of Engineering of the University of Porto and researcher at LIAD in ESCTEC. His main research interests concerns predictive learning with special interest in ensemble learning, with applications in things such as intelligent transportation systems and human activity recognition. He is co-author of an important book, A General Introduction to Data Analytics, which we may recommend. Today, João will talk to us about an ensemble of autonomous autoencoders as classifier for human activity recognition. João, thank you very much for having accepted our invitation to give a talk at DaSSWeb, and the floor is yours.
Thank you for the invitation, and well, I will start by saying that when choosing the subject for this talk, typically I do presentations on intelligent transportation systems because I always worked on it, and I have several works long time on that subject. But today I decided to change a bit the topic, and I will talk about a research line that I'm following. There is some time, and nowadays I have 3 PhD students also working on these subjects, so I think it's interesting also to talk about this. And so I will start by talking about where all this started. This started in a project that was financed by FCT, the Context WA project that already finished in the end of 2019. Despite that, we still have people doing research as a consequence of this project. This project involves in ESCTEC, in ESC Lisboa, and Altis, and the principal researcher was João Paiva Cardoso, that is from my department here at faculty. I was responsible by the machine learning component of this project, let's say, and our goal and our big objective was to create an autonomous human activity recognizer that could be used in smartphones, basically. And in order to do that, that implies many things, much more than what we can think at the first glance. The first thing is that if you download an application with your smartphone with a recognizer like the one we intend to implement, there is no guarantee that it will work well for you, because you can have let's say, some problem in your leg or something like that. So the signal that we produce can be different and is typically different for different people. That implied typically the use of semi-supervised learning, in the sense that the classifier should be able to collect data from the person that is being used in order that classifier has more and more instances, is trained with more and more instances from the produced by the person that is using that classifier. Of course, there is also another subject that is important in a thing like that, is novelty detection. Why? Because there is always a new activity that can be done, or jumping from a plane, or riding bicycle, or whatever. Each person has a set of activities that some of them are not so frequent, and let's say the recognizer should be able to identify them, even if they were not used to trained classifier at the beginning. That imply novelty detection. And there is another thing that is quite important and probably something that is not being so studied. That is the question of the resources that we waste when we are using a classifier. The energy of a smartphone is important. If you, for instance, use a classifier that fades your battery in a short period, you will not use classifier anymore because that is important for you to keep the battery of your smartphone using. So there are things interesting that is sometimes by small adjustments to the hyperparameters of a classifier, we can save energy. For instance, this is just an example. That is something that we should take care of. So let's start with a very simple example with only 6 activities, quite usual ones, walking downstairs, upstairs, walking, jogging, standing, sitting. And we are using three sensors, data from 3 sensors that typically exist in smartphones: the fluorometer, gyroscope, and the magnetometer. Our first work, this was a work already done some years ago, in 2017 or something like that. We have done an ensemble with 3 online methods: K-nearest neighbors, very fast decision trees, and IVBys. And this, we name it the ETVN ensemble, based on this. And this, the combination of democratic co-learning and tree training. Basically what it does is, if 2 classifiers give the same prediction and another gives a different one, we give as prediction the one given by the 2, or if all give a different prediction, we can use confidence given by each of them in order to give the classification. And this can be, and we use it as a semi-supervised method. How? We define a threshold that is the minimum confidence that typically is set to 99%. And we say, if the prediction is given with a confidence equal or larger than this user-defined threshold, we will include this instance using as label the predicted label. So the ETVN has some components that are important to understand. The raw data is stored inside in Windows, and let's say, and the different windows can be overlapped or not. We can control this with 2 hyperparameters: the window size and the overlap factor. Okay. We can have also a step to pre-process in order to reduce noise. But what is more important is that using this kind of algorithms like KNN, very fast decision trees, IVBys, or others, typical machine learning methods, we need to extract features. That is, we need to collect, for instance, to calculate means, standard deviation, correlations, etc., or time domain features, in order to build our own data set with these features extracted from this raw data. Okay, in the work we have done, we have done that. That was we have extracted all these kind of features. And this is done, and that's it. In the test phase, only the instances, that is what I already said about the semi-supervised step. So only the the instance is classified with a confidence larger than a predefined threshold are included in the training. Here is an image of what I have described. So the window segmentation and overlapping is where we define the windows and the overlapping factor. This is the pre-processing to reduce noise. Feature extraction is where we extract data from raw data in order to build these features. And then we train the model, and we have the, let's say, the ensemble that is constituted by 3 different models. The online phase does basically the same, but here the difference is the following. We do the predictions with 3 models. We define the activity based on the given threshold. We see if the confidence is larger or not than the threshold, and if yes, we will include this instance in our, let's say, stream to train, to pass to be included in the training. That is the, let's say, the process that we have used in this method. But of course, one of the things that before saying that, we tested the impact of some hyperparameters with this method, and we found 3 things that are interesting. I think that is the ETVN accuracy is more sensitive to data from different users, the window size, and the overlapping factor. Just a note, there is Paul Pisani that he did work on in order to recognize people. He did his PhD on it, and he was able to see that by analyzing the signal that people produce when walking and on the activities they do, he was able to identify the persons with, I don't remember exactly the accuracy, but a quite interesting level of accuracy based on these signals, just to say that differently that we can think, the way we move give us a kind of identity that sometimes we don't think like that. So our lessons from this is that one of the things that could be important was to automatize the feature construction, feature extraction. And one of the ways to do that is using autoencoders. Here is a representation of an autoencoder. I believe that people know what an autoencoder is. It has 2 components, the encoder component that basically compresses the information in a much lower number of neurons, and then it decompresses it decodes in order to reconstruct the input. Let's say the goal is that the output stay as close to the input as possible. So let's say, talking now about the method I want to talk with more detail, that is the ensemble of autoencoders. This ensemble has, let's say, 2 different parts, one offline and one online. The offline phase, basically what it does is the following. It takes all the data we have for training, and we split it by class, let's say by activity. And we build an autoencoder for each different class. So if we have 6 activities, we will have 6 autoencoders. In the online phase, as new data arrives, we feed each autoencoder with that instance. That is important to say, that raw instance, let's say, without creating new features. Then what we see is which is the autoencoder that is able to reconstruct that instance as closer, as much as possible. That corresponds to the one that obtains a minimum error. And that is the respective class is the predicted class. In this approach, we can also use an online component. And what we do in that case, we also define a threshold, but in that case is a kind of upper limit for the error. We should enforce that we only use that instance for training if the reconstruction of that instance not exceed a predefined threshold for the error. That typically is a kind, typically 1% or something like that. Here is the image that can give an idea of how this works. And there are some things that are important to talk. An important difference to ETVN is that it is not necessary to extract features from raw data. It works directly with raw data, let's say, avoiding one pre-processing step, what is important. Like the ETVN, it also has a window size and an overlap size, and the t-threshold, despite t-threshold has a different meaning in both cases, to be defined as hyperparameters. And I have here also some details about the autoencoder. I will not explain all these details. I think it's not so important, but if you want in the end, I can show it. I can say that we have used an autoencoder with 8 hidden layers, of course, with symmetric, let's say, the decoder and the encoder and the decoder are similar, each one with 32, 80, 80, 100, and 200 nodes. The input had 480 nodes, and I can explain why. We had defined in the experiments that I will describe next a window size of 160, and we use only, in order to compare with other algorithms, only the accelerometer. The accelerometer has 3 axes, so 160 multiplied by 3 axes give 480. And that's why we have used the input with 480. Okay. So in this example, you can see that let's say, the original signal is the red one, and the blue is the result of using each of the 6 autoencoders. You can see visually, easily, that there is one that is that seems to be more, let's say, that has a lower error than all the others, that is seating, and in that case, seating is the predicted class for that instance. Okay. So here, the idea is not that you read all this. These are references. These references are the references of the baselines we have used, just for to facilitate the identification, we used the first name of the author to identify the baseline. All these baselines are, let's say, state-of-the-art for human activity recognition, and the first 5, all except the last one, are neural networks, deep learning approaches for human activity recognition. The ETVN is the one that we have, that is of our own method that we have done previously, that I have already described. Here are data sets. We have used 3 data sets. These data sets, each one have different number of one with 6 activities. That is the one I have used with as example with them, and there are 2 other with 12 activities. One of them have 18, but we have used only 12 due to the scarcity of instances from 6 of them. This is, let's say, the data sets we have used. One thing that is important is, especially in the wisdom, you can notice that there is imbalance in the data. You can see that there are clearly 2 major classes, and that there is especially, there are here some of them that are a bit clearly, seems to be clearly lower. 4.4% is in 5.5 is clearly lower. So in the experiment, the experimental setup, we had a fixed window size of 160. Of course, this represents a different time lag for each data set, because that depends on the frequency that was used for this in each data set, that in one case was 20 Hertz, in another 50, in another 100, so represents different a different time lag. The overlap factor was used always of 20%, and the resampling method used was leave one user out. What is that? That is important in this context. As I told previously, the signal of the users is quite different from user to user. And what we do is, when we test a user, we don't use data from this user for training. And we all use the instances from all the remaining users for training, and we train with that user. And we do that in a cross-validation manner, leaving always a different person for test. Okay, so the data, the methods that we are using never use data from the person that is being used for testing. And the error measure is the mean absolute error that we have used. The results are here shown. You can see here that, let's say, in this example, let's say the ensemble of autoencoders is, let's say, competitive. It's not the best. The ETVN in this case is not. It is not so good. But one thing that is interesting is that the variance here, you notice that is a bit lower than of the other methods. In MLs, let's say the ensemble of autoencoders is very competitive, is clearly the best. method. Also, let's say, please note that we have here two different methods, ensemble of autoencoders and ensemble of autoencoders off. This off means that we don't use that online approach that let's say that put in the training set the instances that were predicted with confidence. Finally, in PAMAP2, that is a quite known data set in activity recognition. A lot of researchers use it. The results were these ones, not so good in this case, or in the average. There is one that is ESO that obtains clearly better results. Ensemble of autoencoders stay more or less together with the majority of the others. It is interesting that ETVN in that case is a bit is better than all the others. What is curious in that case. One interesting that is important to note is, please note that confusion metrics, the results are presented is the precision per class. Let's say if you sum up the values, that gives 100 for each line, for each row. Okay. What it means when this value is lower than 1. It means that the columns are the true values, the rows are the predictions. So it means that the number of true values of the class downstairs is lower than the number of predictions. That there was more predictions in this class than the real number of elements in that class. What you can see is that the two majority classes where you expected, that is the typical behavior in imbalanced data sets, that the major classes have more predictions. In that case, you can see that in jogging and in walking, you can see that in that case, the predictions are lower than the number of real cases that show clearly that the unbalance does not affect these predictions. In the MLs, that is not so evident because it's much more balanced. But if you see, for instance, in PAMAP, you can see this peculiar case that there are two major classes, and in one of them, the number of predictions is higher than the number of real cases, but in the other is lower. So there is not a behavior, a typical behavior that you would expect in an unbalanced data set with this method. And that, let's say, will drive us in a certain direction that is following. That is, these approaches can be, and I think, and I have in this moment a PhD student working on this, exploring this kind of methods, not only this one, but modular classifiers in general, in order to see how they behave for multi-class imbalanced data sets. There is quite a recent paper, I don't know if it was from 2020 or 2021, that is an ensemble of one class SVM for imbalanced data sets. It was published quite recently, but this area of modular classifiers could be more explored for imbalanced data sets, in my opinion, and we are working a bit on this. Please note that that is, I think it is important, that is, in this method, the signal that we produce with an autoencoder does not depend, let's say, is always a single signal that independently on the number of the instances that were used to train that autoencoder. That means that there is no way that the number of instances can be damaging the predictions somehow. For instance, if you are using one class ETVN, each class can occupy more space, more one than another. But in that case, no, let's say. And what is interesting from that point of view. Another interesting aspect is that it deals directly with raw data. It is a characteristic that comes from this deep learning approach. And another interesting, in my opinion, quite peculiar thing is that we can work with each class separately. It's very easy to parallelize, for instance. It's very easy that you can retrain one model, one single autoencoder without retraining all the others. So it's very flexible at that point of view. And of course, all the things that we have done on this, that has involved several students and a lot of people working on this. But, and there are some research lines that we are following on the sequence of these works. I have, let's say, three PhD students working in these topics. Let's say, one of them is working three first topics that I have here. That is the question of prototyping data is being more and more important as we have much more and more data. I can give you an example. I'm working with data from another project that is the project from Safe Cities. It is a big project from a company, a Bosch company, and they have a lot of sensors, and they collect data. Depends on the sensor. It can be every 15 minutes, half an hour, 1 hour, depends. But in the end, they stay with really a lot of data, and the amount of data they need to store is for them really a problem, even because that imply everything is more costly, even the training of the models, everything. And the question is, can we maintain the same characteristics of the data, but instead of storing all this amount of data, just storing part of it that is connected with prototyping? That is an area that is, for instance, for KNN is studied there is already a long time, and it's important, for instance, for time series, but also for KNN, for online classification. If we can predict well with KNN using less distances to calculate the class to predict, the better. And that's it. Another subject that I have already talked about, I have two students working on this, that was quite inspired by these modular classifiers, is on multi-class classification in unbalanced data sets, that I believe that these modular classifiers can have a word to say about this. Well, I don't know if I have talked too much or too less, but I would finish my presentation.
Thank you very much.